welcome to the Deep Dive. Today, we're looking at a truly unexpected approach to maybe the biggest problem in physics.
Unifying quantum mechanics and general relativity. Yeah, it's the Everest of physics, really.
Totally. And the approach. It's called Fox's Quantum Geometry of Information Model. Comes from Travis Mansfield Fox of Jasonville, Indiana.
Right, and the story gets wilder, apparently developed using a cheap cell phone and some AI assistants.
This sounds improbable, doesn't it? But look, our goal here isn't to judge that part just yet. It's to explore the ideas themselves.
Exactly. We've got these documents: refined information unit properties, refined quantum gravity system, and refined calculations.
So our mission for this deep dive is to unpack those, see how they connect or maybe don't connect to establish physics, and figure out what it might mean for you thinking about, the cutting edge.
Let's do it. Where should we start? Those unit properties.
Yeah, let's start there. Refined information unit properties. The model says reality is built from these fundamental units.
Tiny building blocks. And they have quantized properties. First up, energy. E equals n times E Planck.
Okay, so energy comes in discrete packets, multiples of the Planck energy. That sounds familiar, right? Planck's original quantum idea.
Absolutely. And it doesn't stop there. Quantized spin 2, S equals m times A over 2. That's core quantum mechanics.
Right. Spin quantization, fundamental stuff. But then it adds something else.
It does. Discrete position. It says position isn't continuous, but comes in multiples of the Planck length, L Planck.
Whoa. Okay. So space itself isn't smooth. It's like pixelated at the very bottom level.
That's the implication. It connects to theories exploring discrete spacetime at the Planck scale, though it's still a pretty radical idea for many.
Definitely. And what else defines these units?
There's dynamic entanglement between them. The degree of entanglement changes over time depending on the units involved.
Entanglement, okay, that quantum connection.
And crucially, an information state, denoted I. Think qubits or some form of quantum information. It really emphasizes information as being fundamental.
This it from bit idea again. Information makes reality.
Sort of seems that way in this model, yes. It's all built from these info units.
Okay, so that's the foundation. Then there's a refined quantum gravity system. What's the big idea there?
The headline grabber here is variable spacetime dimensions. D equals D of P. The number of dimensions isn't fixed. It can change locally depending on where you are.
Variable dimensions, like 3 dimensions here, maybe 4 or 5 over there?
Conceptually, yes. It's something explored in, very advanced theoretical models like string theory, but it's complex stuff. It suggests space-time is way more dynamic than we usually picture.
Okay, that is mind-bending. So we see bits of Planck, quantum mechanics, maybe string theory ideas woven together.
Yeah, it's pulling from established concepts, but combining them and adding these other layers like discrete position and variable dimensions.
Now, let's get into the refined calculations.
Yeah.
This seems to be where the mechanics are. There's this local space-time value, LP.
Right. And how it's determined is fascinating. There's a perception function, PUP. It depends on the unit's energy and decays exponentially over the Planck length.
So it's like how much a unit feels its neighbors, but only the very closest ones.
Kind of, yeah. Plus a fluctuation function, FP, to account for quantum uncertainty, those random jitters.
And this LP value, it determines the local spacetime, suggesting spacetime emerges from these units.
That seems to be the core idea. Spacetime isn't the stage. It's built by the actors, by these information units and their interactions. Emergent spacetime.
And the calculations link this LP to the metric.
Exactly. The spacetime metric m, which defines geometry distances, curvature is given as a function of this local value, MP.
And this can lead to issues, singularities.
Potentially, yes. The model notes singularities might occur if the absolute value of LA gets too large. And interestingly, the local dimensionality at DPP is supposedly extracted from this metric.
So geometry, dimensions, everything arises from this underlying information field.
That's the picture it paints. It also includes conceptual entropy, H, linked to energy and spin, maybe a measure of system activity, and standard information entropy, based on the qubit states.
And the units move. There's dynamics.
Yes, time evolution. Units are proposed to move along the gradient of LP, like rolling downhill in this space-time value landscape. They exchange energy and spin, and their entanglement and information states evolve, influenced by LP.
Wow. It's a complex, interconnected picture. Units influencing space-time, space-time influencing units.
And they form connections based on entanglement and distance decay, creating a kind of network.
Okay. Deep breath. It's a lot to take in. Now, the elephant in the room, simulating all of this on a cheap cell phone.
Yeah, that's where you really have to pause. Simulating any quantum gravity model is incredibly demanding computationally.
Because you're dealing with the Planck scale, right?
Yeah.
Tiny distances, tiny time steps.
Exactly. Plus dynamic entanglement, a metric that's changing everywhere, potentially variable dimensions, quantum information evolving. The resources needed are usually enormous. Supercomputers.
So the idea that this could be done on a mobile device, even with AI helping, it seems unlikely.
Extremely unlikely with current or near future mobile tech. How the AI agents are meant to interact outside the simulation environment on a phone is also very unclear. Major skepticism is warranted on the simulation claim.
Agreed. But let's bracket the simulation feasibility for a second. What about the model conceptually? Is there novelty here, potential?
Well, setting aside the origin story and simulation claims, the combination of ideas might be where potential novelty lies. Emergent spacetime from information, variable dimensions linked to a local value, the specific dynamics.
If it could be rigorously developed, mathematically sound.
That's the big word. If it holds up mathematically, it could offer a fresh angle on quantum gravity, on how space-time emerges. That variable dimension idea is particularly wild. Could it have implications for cosmology, the early universe?
But it's a huge leap from a set of ideas in these documents to a proper, testable scientific theory.
Absolutely massive. It needs rigorous mathematical formulation, internal consistency checks, peer review, and ultimately testable predictions. That's the gauntlet any new theory has to run.
Okay, so summing up this deep dive, we've explored Fox's model, this unusual blend of quantum ideas, information theory, emergent space-time, variable dimensions, all originating supposedly from a very unconventional setup.
We've seen connections to established physics, but also these really novel, perhaps speculative elements like the local space-time value and its role, and of course serious questions about the claimed development method.
Right. The feasibility of the cell phone simulation seems, well, questionable at best, which really highlights the critical need for scientific rigor, for validation, for reproducibility.
Couldn't agree more. Ideas are fascinating, but science demands evidence and testability.
Definitely. So the thought we want to leave you, our listener, with is this. Could truly game-changing ideas sometimes come from unexpected places, outside the usual channels, even if validating them is a long, hard road?
And perhaps more fundamentally, if information is truly at the heart of reality, as models like this, however speculative, seem to suggest, what does that imply? How might we explore that idea further, maybe even using tools or approaches we haven't fully considered yet?
Something to ponder. Thanks for taking this deep dive with us.